So today we are going to cover lecture number 9, fan duct system. Well, as you can see that, let's see if I can make this smaller. As you can see that in a typical in the typical air side of the conditioning system, we have obviously supply air, return air, and so the air will travel through the air conditioning system. So and we know that the power to supplied into the airstream that can make it move around the air conditioning system is this fan installed in the air handling unit here. So in designing the HVAC system, we will not only try to design all the states, including the supply air states, off-coil states, fresh air ratio, volumetric flow rate. We also need to design the duct system and the fan system. This is the reason we will need to learn the fan duct system as shown in this lecture. Okay, so both of the CAV system and VAV system, as we have already covered, will have air handling units inside for the system. And also for fan coil system, if we use this primary air fan coil system, that means we have a primary air handling units for the whole system before it can supply air to individual fan coil units in each room. So air handling units might also exist in fan coil unit systems. So to learn the fan duct system, we will learn through duct resistance. This is the first topic. And then the fan characteristics. So once you understand the duct resistance and fan characteristics, we connect them together. We connect these two components together, and that will form our fan duct system. Okay, so first we are going to cover the duct resistance. As you can see here, this is a duct as shown, and the volumetric flow rate is V dot, and the unit is cubic meter per second. The diameter of the duct is D in the unit of meter. So when the air travels through the duct, since our surface is, you see, since our well, it can. Okay, the pen does not work. Let me see if I can. So the surface is not 100%. Sorry. The surface is not 100% smooth. So this is why when air is supplied to the duct and it travels along the duct, we will have friction in between the air and the surface. And that friction is the source of duct resistance. So because duct resistance exists, when air travels through this duct from section number 1, as you can see here, and section number 2, from this location to this location, when it travels through the length to be L, we will have pressure loss between these two duct sections, as shown here. So the pressure loss is, we use delta P total from section number 1 to section number 2 as this is the symbol to represent the total pressure loss. And we can see that first you will need to indicate that this is a total pressure, not a dynamic pressure or velocity pressure. And then you will have to mark the sections that the air travels between. So we know that from here, the air travels through section number 1 to section number 2. And the unit of this total pressure loss between the duct sections is Pascal, as you can see here. So when we try to analyze the total pressure, it's actually related to all the parameters that has marked here. So it's related to the airflow rate, the length of the duct section, and the diameter of the duct section. And we normally can make an analogy of this duct resistance to electric resistance. So as you can see, we can use this R to represent the duct resistance in this scenario. Okay, so let me see. I'll have to pause a second to see if my pen works or not. Okay, so to express the total pressure loss between these duct sections, it's related to the it's related to this friction factor times the length of the duct section divided by the diameter of the duct times density of the air or of the fluid divided by 2 times the square of the velocity. So we can see that in this function we have a friction factor, and it's positively related to the length of the duct section, and inverse related to the positively related inverse of the duct diameter. And density is a property value, so this is a fixed value for a certain fluid, and this is velocity. So I will write it like this. Velocity is related to the flow rate of the air that goes through the duct. And we can further express this velocity into a function of the flow rate. So in calculating the air flow rate, we know that it's equal to the velocity of the air times the area of the cross section. And the area of the cross section is related to the diameter. So as the diameter is given here, so the area can be explicitly written out. So this function further equals the friction factor times the length divided by the diameter times, so it's the same here, but for velocity, it's 4 times the airflow rate divided by pi times the diameter of the round duct, and you take the square. And then it actually equals 8 times the friction factor divided by the square of pi divided by the diameter to the order of 5, and times the square of the airflow rate. So when we make an analogy of the total pressure loss with thermoelectric, then we can further express this equation into R times V dot square. So you can see that this term here can be expressed with the symbol R here, and this term is actually equal to the duct resistance. So this is the definition. This is the definition of duct resistance and how we express the duct resistance. And it's used to calculate the total pressure loss between two duct sections. Okay, now we will be moving on to the system resistance. Here? Well, you don't have to worry. I will upload the scripts afterwards. Okay. So for the system resistance, as you can see, because when we tackle the last slide, we know that the total pressure loss is positively related to the duct resistance and positively related to the square of the flow rate. So what we do is we can plot the relation between this total pressure loss and the airflow rate. And the duct resistance actually is a fixed value for each duct section. As you can see here, the R resistance equals 8 times friction factor divided by a parameter and divided by the D of in the order of 5. So for each duct section, diameter is a fixed value, and friction factor also a parameter for each duct section. So for each duct, that means for one specific duct, this value here, R, is a fixed value. So this is the reason why we can plot the two system or two duct here. So we have one duct system with the duct resistance to be R1, and another duct system with the duct resistance to be R2. when R2 is larger than R1, and the relation between the system resistance delta P total for duct number 2 will follow this curve. And since R2 is larger than R1, so this curve will be at the same airflow rate. The value on this curve will be larger than the corresponding value at the second curve. Sorry. This is for the the duct resistance. Okay, so if it's for under the same flow rate, since R2 is larger than R1, so delta P total for duct section for duct system number 2 will be larger than the duct system for duct section number 1. Okay, so this is how the duct resistance can be plotted on one figure. Okay, so now we are going to cover the duct resistance, have duct sections connected in series. So you can see that this duct system is consisted of 3 sections, section number 1, number 2, and number 3. Each section, the duct resistance is R1, R2, and R3 respectively. And then what we do is we actually have delta P1. So it should be delta P total 1, but for simplification, I'm going to just write delta P1. So delta P1, delta P2, and delta P3. And we know that we can make analogy of the duct resistance with thermal resistance and also electrical resistance. So this is the reason why when we get this schematic of the three ducts connected in series, we can actually draw the resistance figure connecting 3 duct resistance together. So our delta P total for this duct section from we have the initial cross section to the outlet or to the outflow will be equal to from this resistance figure delta P1 plus delta P2 plus delta P3. And from the previous expression, we know that for each individual duct section, this delta P will be R times the square of the flow rate. So for delta P1, it will be R1 times V dot square. And for delta P2, it's the same. So it will be R2 times V dot square. For delta P3, obviously, it's R3. It's R3 times V dot square. And since the 3 duct sections are connected in series, so obviously, originally it should be V dot 1 for delta P1, V dot 2 for delta P2, and V dot 3 for delta P3. And since these 3 duct sections are connected in series, so V dot 1 actually equals V dot 2 and V dot 3. And all of them equals V dot, as shown here. So what we can do is we can add them together. So it will be R1 plus R2 plus R3 times the square of the flow rate. So from this expression or an analysis, we can conclude that the sum of the flow resistance some of the equals R1 plus R2 plus R3. So this is also the reason why we can write out or we can draw the resistance figure as shown here. So this is the duct resistance when we have duct sections connected in series. And actually, we can also draw the figure between the total pressure and the volumetric flow rate on a chart shown here. So the original three duct resistance expression or system duct system expression for number 1 duct section, number 2 duct section, and number 3 duct section are shown here as an example in this blue dashed line. So once this R value is given, then you can draw the corresponding system curve here. And when we connect these three duct sections together, what we do is we find for example, for each specific volumetric flow rate, as shown, for example, in this corresponding V dot value here, what we do is we find delta P1 for duct section number 1 and find delta P2 for duct section number 2 and also find delta P3 for duct section number 3. And then we still follow this line and we find the corresponding P total value that satisfies delta P total equals delta P1 plus delta P2 plus delta P3. And this is how we determine the delta P value for the duct section with when the corresponding volumetric flow rate is V dot here. And what we do is we do that for, we follow this procedure for different V dots, and this is how we can obtain the system curve as shown in the red line. Okay, so this is how you can express the duct resistance in series when we have duct sections connected in series. Okay, now we will be moving on to the topic of duct resistance connected in parallel. So similarly, we have two duct sections, section number 1, section number 2, and section number 3. And for section number 1, the flow rate, air flow rate is V dot 1. For section number 2, the flow rate is V dot 2, and the section number 3, the rate is V dot 3. And we also have individual duct resistance values R1, R2, and R3 for each of the duct sections. And the total volumetric flow rate is a V dot. So obviously, first of all, from mass balance, we know that V dot equals V dot 1 . Well, my pen stopped working again. Okay. plus V dot 2 plus V dot 3 according to mass balance. So this is the first equation. And the second equation is we look at the total pressure loss. Since all the three duct sections are connected in parallel, so the pressure difference between these two sections for duct section number 3 equals this delta P for duct section number 2, and further equals delta P for duct number 1. And also, this delta P is the same for the system of the three connected duct sections. So that means so that means delta P total for the system equals delta P delta P1 equals delta P2 . So I really don't know what happens now. But anyways, I'm going to use my finger. Okay, so delta P number 2 and further equals delta P number 3. So this is the second equation for the duct resistance connected in parallel. So what you can further do is you can express this delta P in terms of the thermal resistance and the flow rate. So delta P1 equals R1 times V dot 1 square. Delta P2 equals R2 times V2 V dot 2 square. And delta P3 equals R3 times V dot 3 square. So that means what you do is you can actually express V dot 1, V dot 2, and V dot 3 with a function of thermal resistance and delta P. Trying again with the pencil. So delta P1 equals R1 times V dot 1 square. So that means V dot 1 equals the square root of delta P1 divided by R1. So we do the same for delta P2. So V dot 2 can be expressed with delta P2 and R2, and delta P3 is the same. So we have V dot 3 equals 3. So since from the second equation, delta P1 equals delta P2 equals delta P3. And also from the first equation, V dot equals V dot 1 plus V dot 2 plus V dot 3. So for the duct system, delta P total equals the resistance of the system. Since this is the duct system connected in parallel, so we have R sub P compared with the previous, we have R sub S for duct system connected in series. Okay. So from the expression, it's actually V dot square. So for the duct system, this is a predefined expression from the definition of the duct resistance. So the duct resistance of the system equals delta P total. No. Sorry, it should be. So we aim to close the equation system. So V dot equals, this is the total volumetric flow rate, equals the square root of delta P total divided by the system resistance of the duct system. Okay. Then we look at the first equation here. For the first equation, the left-hand side is the total volumetric flow rate, and we can express that with this expression here. So this is number 1, 2, 3, 4. So basically, we substitute 1, 2, 3, 4 into equation number 1. Okay, so we substitute 1, 2, 3, 4 to equation number 1. So on the left-hand side, we have the square root of delta P total divided by R sub P, and in the right-hand set, well, it stopped working again. In the right-hand side, the delta P1 divided by R1, and the second term is delta. And the third term is delta P3 divided by R3. So we further look at this equation, and from equation number 2, we know that delta P total equals delta P1 equals delta P2 and equals delta P3. So in this equation, the terms on the top, on the upper part, can be canceled out, or you can divide the whole system. You can divide the whole equation with the square root of delta P. And then you will be left with the square root of, or I'm going to write like this. The inverse of the square root of the duct system resistance equals the inverse of the square root of the first duct section resistance plus second duct resistance plus that for the third duct resistance. So this is the expression of the duct system for ducts connected in parallel, and its relation between the original 3 duct sections duct resistance. So that's for the duct resistance connected in parallel. And the resistance profile on this chart, with the horizontal axis to be the flow rate and the vertical axis to be the total pressure loss. Then, first of all, we are also given with the 3 resistance value for 3 individual sections. So we can first of all draw or plot the figure for 3 duct sections with these 3 blue lines here. And then what we do is we do not want to go through all the calculation process, but we would like to plot the duct resistance on this chart directly. So what we do is we find a certain pressure drop, and on this constant pressure drop line, we find the corresponding flow rate value for duct section number 1. So we have V dot 1, and for duct section number 2 with the second blue line, and we find V dot 2. And at last for duct section number 3, V dot. So what we do now is since the 3 duct sections are connected in parallel, so V dot, the total V dot equals V dot 1 plus V dot 2 plus V dot 3. So on this constant pressure drop line, we find this corresponding value with the value of the flow rate to be V dot 1 plus V dot 2 plus V dot 3. So that means with these 3 lines, we can first of all find these 3 dots here, and with the corresponding value of these 3 dots, we can locate this 1 dot. And this 1 dot is only for a certain corresponding total pressure drop. And what we do is we do that for different pressure drops, and by moving along the total pressure drop axis, we can find the corresponding volumetric flow rate each time, and we connect these obtained dots And finally, we can get the system curve as shown here in this red line. Okay, so this is for the first of all, the definition of duct resistance and the expression of duct resistance, and how you can calculate the duct resistance of a duct system when we have, for the first scenario, when we have duct sections connected in series, and the second scenario when we have duct sections connecting in parallel. And then we will be moving on to the next slide when we can actually calculate the flow resistance in a duct system on this example. Okay, we will briefly introduce the given conditions of this example, and we will have a break, and after that we will continue our lecture. So in this duct, this is actually a very normal design. We can see a duct section from 0 to 1 as a primary duct or a main duct, and then it's separated into two it separates into two smaller ducts. So the total volumetric flow rate of the main duct is 1 cubic meter per second, and then it's distributed to two separate duct sections with 0.5 cubic meter per second for each duct section. So once we get this problem statement, what we can do first is we can draw the duct system resistance figure as shown in the right hand side. So we start with the resistance of a duct section from 0 to 1, and the corresponding volumetric flow rate is V dot 0 to 1. And we have a dot 0 corresponding to the cross-section 0. And we have dot 1 corresponding to cross-section number 1. And then as the cross-section number 1 is where the duct is split into two individual ducts. So for duct 1 to 2, we have the resistance to be R1 to 2, and the corresponding volumetric flow rate is V dot 1 to 2. And similarly for duct section 1 to 3. Okay, then we can actually use the system resistance figure to find the system curve as shown in the red line here. So first of all, we actually started with A, B, and C. So two dashed blue curve and one orange curve here. And then we can, by two steps, we can obtain the system curve as shown in the red line. Okay, it's 9:25, so we will have a 15 minutes break and we will resume our lecture at 9:40.